you want to be able to solve an nth order linear differential equation here with constant coefficients. Constant coefficients simply means that in front of each derivative, like y prime, y double prime, y triple prime, in front of those, there's a number. So there's no variable, it's just a number. So this is it's the easiest form that we would examine, but it becomes the model for all the other forms. It becomes a very strong foundation. We can solve based on what we call an auxiliary equation. Our goal is to be able to solve equation number 1, said to be the homogeneous nth order differential equation with constant coefficients. So the a sub naught, a1, a2, and so on to a sub n, those are just numbers. Those are just numbers. If I have that type of equation, we can solve based on this method in 4.3. I give an example here. To solve equation number 1, you first consider the very simple case, let n equal to 1. That is the differential equation with a first order differential equation, a first order derivative in it. So that becomes basically some constant times y prime plus a constant times y equal to 0. You can separate the variables if you do that. Separate the variables to solve, and we did that. Very simple problem going back to the first part of chapter 2. We solved that, and we got y equal to some constant times e to here, based on these numbers here, negative b over a. Basically, you divide through by the a, and so we get y equal to c times e to the negative b over a times x. Typically, I work that all out, but I thought best to put it right here. And just type it out for you. Suppose m, a constant, is equal to negative b over a, which is also a constant. Then the solution type is y equal to some constant times e to the mx. What we're saying here is that then becomes the model of solutions for even the higher order differential equations. Here, this is n equal to 1. What happens when n is equal to 2? What happens when n is equal to 3? The solutions still look like this form right here, y equal to some e to the mx. Well, if that be the case, then we assume that the solution type is y equal to this e to the mx. So now let n equal to 2, just going up in that order. Let n equal to 1, see how the solution looks. Let n equal to 2, to see how the solution looks. You let n equal to 2, we get a lot of stuff. So we spend time with that, and we don't worry about getting to n equal to 3. We're going to just camp right here and make a good church right here with n equal to 2, Missionary Baptist Church. Right? That's what we'll do. So if that be the case, the equation that I have that I want to solve is a times y double prime plus b times y prime plus c times y equal to 0. I want to solve that. If we let y equal to e to the mx, and we say that this is the solution type, that y equal to e to the mx is a solution type, then let's take this y and plug it back in to this equation number 2, and what happens is you produce an auxiliary equation. Let me show you. I'm putting it there, but you want to be able to see it. Again, this is the introduction. So let y equal to e to the mx be a solution type for equation 2. Well, that be the case, then y prime is equal to m times e to the mx. And y double prime is equal to m times m, or m squared, times e to the mx. So I'm going to take equation 2, which says a times y double prime plus b times y prime plus c times y is equal to a times y double prime, well, that's m squared times e to the mx, plus b times y prime, that's m times e to the mx, plus c times y, and that's e to the mx. Well, this is set to equal to 0 from equation number 2. We're solving the homogeneous differential equation. Notice that I have something common there. I have an e to the mx is common. This is e to the mx that I factor out times brackets a times m squared plus bm, it's a sorry looking m, plus c is equal to 0. Well, since this exponential form e to the mx is never equal to 0, it has to imply that a m squared plus bm plus c has to equal to 0. Right? Since e to the mx is never equal to 0, this implies that a m squared plus bm plus c equal to 0. We call this the auxiliary equation. It's a derivative equation from equation number 2. Right? It's not equation number 2. It's an auxiliary equation. I have to remind the church that you are an auxiliary. You don't run the church. You're just the homecoming committee. You're an auxiliary. Right? So the auxiliary equation will help us to solve number 2, right? But this auxiliary equation is not the differential equation. Understand that. All we're trying to do with the auxiliary equation is to determine the value or the nature of m. Because the m's go back to that e to the mx, which becomes a solution to whatever differential equation that I'm looking at. If it's a linear differential equation with constant coefficients. So this here is said to be the auxiliary equation. There are 3 possibilities for the choice of m. Again, our purpose of taking the equation number 2, working on it to get this auxiliary equation, is to find the values for m. There are 3 possibilities for m. There was an old deacon down at John the Baptist Church in Oroville. I wasn't a member of the church, but I loved to go out there sometime. I had an old deacon named Mr. Manuel Colin. That's how he would express himself. Church, I want to tell you that God is, man, I just loves that old man. He said he had something like called pink liver or something. I don't know what that. Anybody ever heard of that before? Pink liver. You don't want to know what that is. But anyway, the choice of m, 3 possibilities. M could be the values of m, they could be distinct. That means they can be different. If I'm talking about a second order differential equation, I'm looking for 2 solutions, at most 2. So my choice for m that would go up in that exponent is 2 possibilities for m sub 1, m sub 2. They could be different. That's one possibility. They could be the same. Second possibility. Or they may be complex conjugates. Right? Now, why is that? Notice equation number 3 is a what kind of equation? Equation number 3 is a what? It's quadratic, right? See, again, equation number 3 is not the differential equation. That's equation number 2 is a differential equation. Equation 3 is an auxiliary equation, which is a simple algebraic quadratic equation. And so for any quadratic equation, there's always 3 possibilities for the solution, right? Either if it's a quadratic equation, you got a parabola, so you can say that parabola can cross the x-axis twice. That means you have 2 distinct solutions. Or the parabola at its vertex can just touch the x-axis. That means that both solutions are the same. You only have 1 solution. or the parabola never crosses the x-axis. That means that the solutions are imaginary, complex conjugate. Same thing. So if they're real and distinct, then let's look at that. And that's just the one problem that I'll work, number one, and then I'll be through for today. And I'll give you a problem that you need to know how to do, because you just may see this again. Yes. Okay. Well, let's see here. Here they don't give me a solution to find a second solution. Here they don't give me both solutions to verify. I got to produce it, right? So here's how you do this. You say let y equal to e to the mx be the solution type. It's not the solution, it's the solution type. Moses is a type, right? Abraham was a type. He was a type of Christ, right? He wasn't Christ. They were not Christ, but they were a type. Noah was a type. All right. So if this be the case, then y prime is equal to m times e to the mx. I got a y prime there. And then y double prime is m squared times e to the mx. Just mimic the proof that I just gave. So here I go to the equation. This is 4y double prime plus y prime. I replace now, substitute 4 times y double prime. That's m squared times e to the mx plus y prime, which is m times e to the mx. Notice I can factor out what's common, e to the mx times brackets. What I have left, 4m squared plus m equal to 0. Well, since, yes, e to the mx is not equal to 0, never equal to 0 for any choice of x that's real, this implies that 4m squared plus m is equal to 0. We just solved for m. Remember, I made a comment a couple days ago, and I said that it's strange, but students at this level, they have trouble with algebra. Remember I made that statement? I was talking about these type of problems right here. Because to solve for m, that's just a simple algebraic equation. Please don't mess those up. At least get the algebra right. Say, look, professor, I couldn't get the DE, but I sure got the algebra right. I give you a couple of points. So here we solve for m, factor out of m, we get 4m plus 1 equal to 0. This implies that m is equal to 0 and m is equal to negative 1/4. So what does that say? That says that y sub 1 is equal to e to the 0 times x. This is e to the 0, that's equal to 1. And this says that y sub 2 is equal to e to the negative 1/4 x. Remember, the type is y is equal to e to the mx. I'm just solving for m to get my solution, right? So you know what that means? That means that based on the superposition principle, that the general solution is here, c sub 1 times 1 plus c sub 2 times e to the negative 1/4 x. That is c sub 1 plus c sub 2 times e to the negative 1/4 x. So all we've done now is we've shown you how you can solve a linear differential equation, nth order, with constant coefficients, where the solutions have distinct values. There's the second case, the solutions said to have repeated values, and then thirdly, the solutions have complex values. We hadn't gotten to those two parts. I'll do that on Monday. Okay? Thank you. Let me turn this off, and then I'm going to give you something, and I need you to work this problem.